So last time we ended with specific heat capacity, and I really want to explain it so that you guys can understand it clearer. Now, if we consider two objects, let's say we have water and we have iron, a piece of iron. Now, if I want to heat up water and heat up iron, you see, if I apply the same amount of heat to both iron and water, it's going to take more time for water to heat up as compared to the iron. And since it's going to take more time for the water to heat up than the iron, then we're going to say that water has generally a higher specific heat capacity than the iron. So that's how the difference comes about. But the question is, how then can we be able to, what ways or various ways can energy be absorbed? So these are the various ways. If you see, it's possible if we increase the juggling motion of the molecules, we will have to raise the temperature. In that way, energy can be absorbed. If we increase the internal end vibration or rotation within the molecules, I mean, these are things I've already explained. We just need those molecules to vibrate. We just need them to oscillate. We just need them to translate. We just need them to have some kinetic energy. And if we can do that, then we're going to see that in that case, just vibrating the molecules, rotating it in whatever way, it's going to increase the energy that is absorbed. So these are the various ways that that can be done. And now, because of what I've explained, now if you compare water and land, you see that the specific heat capacity of water is higher than the specific heat capacity of land, because if the same solar radiation or sun rays is hitting on the water and on the land, you see that it's going to take less time for the land to heat up compared to the water. It's going to take more time for the water to heat up, and these indifferences in the amount of heat that an object is going to receive to heat up brings about what we have: different climates and different conditions in different places in the earth. Now, for places where it's very mountainous and there's less water, it's going to take more time for those to heat up. In places where it's more watery, we're going to take more time for the water to heat up, and that's this imbalance in this process comes about with the different climatic conditions we have in maybe in North America or in South America and in different regions of the world today. So let's try to answer this question. Which has a higher specific heat, water or land? Which obviously, like I said, the answer will be water, obviously, because it takes more time for water to heat up as compared to land. We've already explained that. Okay, let's see. So the next thing that we're going to look at it's thermal expansion. So what will cause an object to expand? And the answer is heating the object. So due to the rise in temperature of a substance, molecules begin to jiggle faster and move far apart. So if you have a molecule, two molecules, if you have two molecules, and you start applying heat, what's going to happen is that at some point the molecules are going to vibrate and going to try to get apart each other, and it's these molecules trying to move apart each other that brings what we call an expansion. They begin to expand. Most substances expand when heated, and most substances begin to contract when it's cool. So an example we can see, it's a railroad tracks closely laid on winter days expand and bubble in hot summer. Warming metal lids on glass jars under hot water loosens the lid by greater expansion of the lid than on the jar. And we can see what happens here when it comes to thermal expansion. The extreme heat on the summer day causes the bubbling of these railroad tracks. So you can actually see what's happening. So what is happening during the summer, there's a lot of heat and the particles in the metal begin to expand and we can see that even the same thing also happens. This gap in the railroad bridge is called an expansion joint. It allows the bridge to expand and contract. So that's why in most railroad we must have these, because if you don't have that, then there's going to be a problem, because there'll be a point during hot summers where the road is going to expand and breaks, and that becomes a very big problem. So we don't want that. So engineers, what we do is we put this railroad gap just to ensure that even when it expands or when it contracts, it's going to keep the road at the same level, where it will not have anything like accidents or anything like that. So Now, let's try to answer this question. When stringing telephone lines between poles in the summer, it is advisable to allow the lines to do what? So if you're trying to string a telephone line between poles during the summer, so we know during the summer what's going to happen, there's going to be expansion. So what are we going to do? So is it as advisable to allow the lines to sag or to be taut or to be close to the ground, or what happens? Generally, the answer is it's better for us to allow it to sag. So telephone lines are longer in warmer summer and shorter in cold winter, hence they sag more on hot summer days than in winter. If the lines are not strong or with enough sag in summer, they might contract too much and snap during the winter, especially when carrying ice. So these are just normal day applications that we use when it comes to thermodynamics. Another question we have here: an egg hits a metal ring that has the same inner diameter as the diameter of the metal ball. When the ring is hot, the room temperature ball, what will happen to the room temperature ball? Fits into the hole as before, no longer fits into the hole with more room to spare, none of this. So what do you think? So an egg hits a metal ring that has the same inner diameter as the diameter of a metal ball. So if it hits the metal ring is going to expand, and if it expands, it means that the metal ball will be able to get into the metal ring. Now, when the ring is hot, the room temperature ball, what happens? Fit into the hole as before, no longer fits into the hole with more room to spare. So guess what? The answer will be fit into the hole with more room to spare, because when you heat it, it expands, like I've explained before. So expansion in metal, it's the same process. So in this case, we have what we call a bimetallic strip, and it's made up of brass and iron, both are welded together. When the strip is heated, brass expands more than iron, obviously. When cooled, brass contracts more than iron. Due to this behavior, the strip bends as shown below. So we have this. If you cool it, the iron is going to brass is going to cool, contract more than the iron. If you heat it, brass is going to expand more than the iron. If it's at room temperature, then we have a situation like that. So well, I can explain this to us, but it's simply based on the principle of expansion of metals due to heating. And it releases the coil when a thermostat, for example, like in the case of a furnace. So when the bimetallic steel expands, the ball of liquid mercury rolls away from the electrical contact and breaks the circuit. So it's just a kind of an application to what we've been talking about in thermodynamics. So expansion of water, the same thing we've been talking about. So this is water, it has different molecules. You see the molecules are close together, and what happens is that if you heat this up, what you're trying to do is you're trying to cause these two adjacent atoms to begin to vibrate and begin to expand or to begin to increase when you heat it up. So, but now when you cool it, what you're trying to do is that you're trying to contract them, so the atoms begin to come closer to each other. So what we're seeing is that when water expands when it turns to ice. Ice has open structure crystals resulting from strong bonds at certain angles that increase its volume. This makes ice less dense than water. So the catch here is that when you expand water, you make it less dense. But when you expand water, you make it more dense. Do we understand what I'm saying? Water expands when it turns to ice, right? Ice has open structure crystals resulting from strong bonds at certain angle that increase its volume. This makes ice less dense than water. I'm going to explain this in further. This is what we call the behavior of water. So generally, we know that the freezing point of water is 0 degrees. So at 0 degrees, water turns into ice. But now there is a problem. At 4 degrees, water behaves in a very different way, in a very abnormal way.